Yes, hello students. In this lecture, we shall discuss the dynamics. In this heading, we shall study steady state stability. We have already learned one equation, that is the dynamic torque equation. T minus TL is equal to J d omega m over dt. So we have seen that when the motor torque is more than the load torque, the motor accelerates, speed increases. When the load torque is more than the motor torque, this term is negative, the speed decreases. And when T equal to TL, then the motor neither accelerates nor decelerates, but runs at a constant speed. That speed we call as equilibrium speed, or you can say that this is the steady state speed. During the difference between T and TL, the transients are there. Motor speed changes, either increases or decreases, but at the steady state stability, the motor runs at a constant speed and the torque is equal to load torque. Now this speed at which the motor is running, that speed may be stable speed or it may be unstable speed, or you can say that the operating point may be stable operating point or it can be unstable operating point. If the speed changes due to some reason, then if the speed is restored back to the original speed, steady state speed, then we say that that speed is stable steady state speed, and that operating point is steady in the stable operating point. On the other hand, if due to some disturbance speed changes and that speed is not, you can say, not restored, and that operating point is not restored, so that operating point will be called unstable operating point, and that speed you can call as unstable steady state speed. So today we shall learn how to find out whether the operating point is stable or it is unstable. For this we have to make a check. The check is that if with the increase in speed the motor torque becomes less than the load torque, then you can say that the point is stable operating point, otherwise the point is unstable operating point. You can see that in this in the motoring mode, the motor torque is a driving torque. Motor torque is causing the speed. So motor torque is the driving torque and the load torque is the braking torque, opposing torque. So when the speed of the motor increases, then what should be the case? The driving torque should be less than the opposing torque, so that the motor speed decreases. So with increase in speed, if the motor torque becomes less than load torque, that is the driving torque becomes less than the load torque, you can say that the point is stable, and because of this difference, speed of the motor will decrease and again it will come back to the original speed. So that point will be called stable operating point. Or if with the decrease in speed, if the speed decreases due to some reason, then if the driving torque, that is the motor torque, becomes more than the load torque, then the speed will increase. This term will become positive, speed will increase and the original speed will again be restored. So you can say that the point is stable operating point, otherwise it is unstable operating point. So another check you can make, you can use either this method, you decrease the speed slightly and see what happens, or you increase the speed and check what happens, or you can make another check that you find out at the point, operating point, the value of dTL upon d omega m, and check whether it is more than or less than dt upon d omega m. If it is more, then you can say that the point is stable, otherwise it is unstable. So this also you can do. Now let us take few examples. I have taken here 4 examples. These two are in the motoring mode. For the case of motoring mode, these two are for the case of braking mode, forward braking mode. Let us take the first case. Here the speed torque characteristic of the motor is drooping, where the load torque is increasing with the speed. So this point is the operating point. This is the equilibrium speed omega ms. At this point the motor is operating. Now we have to check whether this point A is a stable operating point or it is unstable operating point. For that, let us slightly increase the speed and see what happens. I will increase the speed from omega m to omega m1. With this increase in speed, for this speed, the load torque becomes TL1, the motor torque becomes T1. Speed has increased, so motor torque has become less than the load torque. When the motor torque is less than load torque, then this means that the motor will decelerate. Speed will decrease, again the operating point will be restored. So you can say that point A is a stable operating point. Suppose the speed decreases. For example, let us assume that the motor speed has decreased to a value, say omega m2. What will happen? The motor torque will change to T2. The load torque will change to TL2. So with the decrease in speed, motor torque becomes more than the load torque. Motor will accelerate, speed will increase again, and the operating point A will be restored. So you can say that this operating point is a stable operating point. Now let us take the second case. In this case, this is the load torque, the motor characteristics, and their load torque characteristics. Now at this is the operating point. This is the equilibrium speed. Now to check the stability, you increase or decrease the speed slightly. Let us increase the speed slightly and see what happens. So I will increase the speed from omega ms to omega m1, and if this is the speed, then this is the load torque TL1, and this is the motor torque T1. In speed has increased. This is increase in speed causes the motor torque to become more than the load torque. This means that the motor will further accelerate. Speed will increase further, and the load torque will become even less, and the motor torque will become higher. And what will happen? The motor speed will never be restored back, and the point B will never be restored. So you can say that point B is unstable operating point. Unstable operating point. Now let's take this case. This is the forward braking mode operation. Motor characteristics, load characteristics. Again, this is the speed at which the motor is operating. Now to make a check, let us increase the speed slightly and see what happens. Increase the speed to omega m1. This results in load torque to become TL1 and motor torque to become T1. T1 is negative, TL1 is negative. T1 is more negative. This means that T1 is less than TL1. So in this, to check this, you have to consider sign also. So in this case, T1 is less than TL1. It is more negative than TL1. So T1 is less than TL1. So the motor is stable. The operating point is stable. So this point C, you can say that it is a stable operating point. You can think in another way also. The magnitude of, with the increase in speed, the magnitude of driving torque should become less than the magnitude of opposing torque. In a forward braking condition, the driving torque is the load torque and the motor torque is opposing the speed. So with the increase in speed, the magnitude of driving torque has become less than the magnitude of braking torque. So speed of the motor will decrease and the operating point C will be restored again. So point C, you can say that it is a stable operating point. Let us take the fourth case. This is a point D. The motor is running at this speed, omega ms. To check for stability, let us increase the speed slightly to omega m1. This causes the motor torque to increase to T1 and the load torque to become equal to TL1. Again, with the sign you have to see. TL1 is more negative than T1. So T1 is actually more than TL1. So with the increase in speed, the motor torque becomes more than the load torque. Motor will further accelerate, speed will go on increasing and the point D will never be restored. So you can say that point D is unstable operating point. Again, think in terms of magnitude. The motor speed has increased. This is causing actually for a stable operation, the driving torque should reduce. The magnitude of driving torque should become less than the magnitude of opposing torque, so that the motor speed is restored back to original speed. But here you can say that with the increase in speed, the magnitude of the driving torque, that is load torque, has become more than the magnitude of the opposing torque or the braking torque, that is the motor torque, and the motor speed will never be restored. So you can say that point D is unstable operating point. So these are four typical examples. You have studied earlier in your previous courses on machine the speed torque characteristics of induction motor. And then you have seen that some region of the characteristics is said to be stable operating region and the other is known as unstable region. So let us try to find out whether that statement that this region is stable region and this region is unstable region, it is correct or not. So we can now check it. We know the technique how to check the stability of the operating point. So let us do it now. Now here I have drawn the speed versus torque characteristic of the motor. So earlier we have studied the torque speed characteristic like this, where we show the torque on this axis and speed on this axis. Speed on this axis and torque on this axis. This speed we called the synchronous speed, starting point. So this was the starting torque. But here in the case of drives, we always take speed on the y-axis and torque on the x-axis, because actually speed depends on torque. This torque, that is the motor torque, depends on the load torque. In the steady state operation, motor torque has to become load torque. So load torque is independent variable. So torque has to follow the load torque. and depending on the torque, motor will have certain speed. So speed should always be a dependent variable. It depends on the torque. So we always take speed on y-axis and torque on x-axis. So this is the speed versus torque characteristic of the motor. And I have taken the case of load torque, which is constant at all the speed. So now you can have two operating points, point A and point B. As per our knowledge, this region is a stable region and this region of the characteristic is said to be unstable region. Let us check whether that statement is correct or not. So let us take point A. Let us check the stability of point A. You increase the speed slightly. So this is the steady state speed, equilibrium speed. We increase the speed slightly and see what happens. Increase the speed to omega m1. This causes motor torque to become equal to T1. Load torque is constant, it's not changing. So motor torque has become less than the load torque, or in other words, the driving torque has become less than the braking torque. So this means that the speed of the motor will decrease and this point will again be restored. As the speed decreases, the motor torque will decrease and finally it will come to this point A, where the speed is, where the load torque is equal to motor torque, and thereafter the motor will run stably at operating point A. So you can say that the point A is a stable operating point. So this is the case whether you take this point or this point or this point. In all the cases, if you decrease the speed to omega m2, you can say that the load torque the motor torque has increased to T2. Any decrease in the speed will cause motor torque to become more than the braking torque or the load torque, and the motor speed will decrease, it will increase, and the point A will again be restored. You can say that point A is a stable operating point. So in the whole region seems to be a stable region. Now let us take the case of point B. At point B, this is the steady state speed. Let me call it omega mb. And suppose we increase the speed slightly to check the stability. So we have increased the speed to omega m1, for example. Omega m1 dash, we call it. The motor torque becomes equal to T1 dash. The motor torque becomes more than load torque. This means that the motor will accelerate, speed will increase. As the speed increases, the operating point will further change. It will increase and finally it will reach at this point where the motor torque becomes equal to load torque, and this will be the operating point. So if you assume that the motor is operating here, any increase in the speed will cause the motor characteristic to operating point to shift from B gradually to point A. And as A is a stable operating point, the motor will afterwards run continuously at the operating point A. So you can say that this is a stable operating point. Now similarly, so you can say that this region is a stable region, this region is unstable region. Now take the second case. Again we have the characteristic of this induction motor, and again we are having two different torques. This is speed dependent load torque. You may assume that this is a fan type load, whereas torque is proportional to square of the speed. So if this is the case, the load torque is TL is equal to some C omega m square. In one case we have one value of constant C, in the other case other value of constant C. So you are having two different fans that will be connected to the motor. So let us take the first case. This is the operating point. The steady state speed at this operating point is omega ms. You may call it omega s. And let us check the stability of this point. You increase the speed slightly and see what happens. Increasing the speed from omega ms to omega m1 will cause the motor torque to become equal to T1 and the load torque to become equal to TL1. So with increase in speed, the motor torque becomes less than the load torque. This means that the driving torque has become less than the braking torque. So the motor speed will decrease and the operating point C will be restored again. So point C, you can say that it is the stable operating point. So this is as per our knowledge that this region is a stable region. Now let us see the operating point D. If the load torque has this characteristics, then this will be the operating point. So let us check whether this point is stable or not. As per our knowledge, this should be unstable operating point. Let us check whether it is correct or not. So we increase the speed slightly to see what happens. Increase the speed to omega m1, say omega m1 dash. With this new speed, the motor torque becomes equal to T1 dash, whereas the load torque becomes equal to TL1 dash. So with the increase in speed, the motor torque becomes T1 dash, which is less than the load torque TL1 dash. This means that the driving torque has become less than the braking torque and the motor speed will decrease. Means that point D will be restored back. So you can say that point D is a stable operating point. So our assumption that, our statement that this region is always unstable region is not correct. So in this situation, point D will be a stable operating point. Point C will also be a stable operating point. The whole region becomes a stable region. So now you can say that it is not always correct that this region is unstable region and this region is stable region. The reverse may also happen. So in the previous case, when the load torque was constant, this is always the case that this region will be stable region and this region will be unstable region. But in such cases, the things may change. Now here again, let us see and assess the dynamics of the motor. Suppose this is the motor characteristics, and you just apply this load torque and start the motor. Then what will happen? You start the motor. This is the load torque. This is the starting torque. Starting torque is less than the load torque. So this means that the motor will not start at all. Motor will remain stationary. It will start drawing heavy current from the source, and if you leave it connected, the motor windings will be overheated and will burn out. So you have to stop the motor immediately if this happens. And you can connect such a load when the motor has started running. You start the motor, give the supply, torque is not connected there, load torque is not there, motor will accelerate and it will reach this operating point, that is near the synchronous speed. Now you can connect a load torque. If you connect a load torque like this, TL, so what happens? Motor is operating at this point, this was the speed, and the load torque is this much. Motor torque is near 0, load torque is there, opposing torque is there, motor speed will decrease, operating point will move like this. It will reach at this point when the motor torque becomes equal to load torque, and that will be the operating point. If the speed tries to reduce beyond this, as soon as we reach somewhere here, the motor torque becomes more than the load torque, motor will accelerate and the speed will again restore to the operating point A. So this is the case. If you further increase the load torque and increase the load torque beyond this point, say you have increased the load torque to this value TL dash. You applied this load torque, motor, you have started the motor, this is the initial speed, then you have applied this load, the motor speed will decrease because the motor torque is less than the load torque. Motor torque is here, load torque is here, so less than the load torque, speed will decrease, torque of the motor will increase, but even at this point, the motor torque is less than the load torque, and the speed will decrease further, and after that, the torque produced by the motor will decrease, and finally you will come to zero speed. Even at zero speed, the motor torque is less than the load torque, so the motor will not operate and it will come to standstill. So such a torque which is more than the breakdown torque, the motor will come to standstill. If you apply this load torque, so this is the breakdown torque. If any increase in the torque beyond this will never satisfy the condition that T equal to TL, and the motor will come to standstill. So that torque is known as breakdown torque. So with this, now you can have any situation, and with this technique you can find out whether the operating point is a stable operating point or it is unstable operating point. Now you can try other examples that are given in your textbook. I shall provide some tutorial sheet. From there you can try on your own the various cases and try to find out the stability of various operating points. So this is all for today. Thank you very much. Excellent.